So now, given that we know what we want to do, the question is, how do we define the support vector machines classifier? So intuitively, our goal is to separate kind of pluses from minuses, right? We want to separate spam email from non-spam email. And the way we will do this is the following. We will think that we are given a set of training data examples, right? This is just a set of pre-labeled emails, right? Every email has a set of features plus the corresponding label, whether it's spam or not. And the way we can think of this is that for every example, right, for every training example, for every email, we have the feature vector that is real valued, and where the squares of the features sum to 1, so it has a Euclidean length 1. And simply we can think that in this case, these features tell me whether certain words are present or not present in the document, and the y is simply the class label, whether this is spam or not. And then, as we said before, the way we will do our classification, we will take this weight vector w and do a product with the feature vector x to make the classification. So now the question is, right, what is the best line in this case that separates out pluses from minuses? And the line, as we will demonstrate later, is actually defined by the weight vector w. And for example, in this small case that I have here, there are many possible lines that separate pluses and minuses. So the question is, which among these three different lines is the best one? So in order to decide which of the three different lines or separating hyperplanes is best to use, let's look at this simple example. So we have non-spam and spam, and we have our separating line between spam and non-spam. Now, the intuition we would like to build here is that the distance from the separating line tells us how sure or how confident are we in a prediction. For example, if we ask, how confident are we that this email A is not spam? That would be very easy. It's very far away from the decision plane. While, for example, for this email C, we are not entirely sure, right? It's very close to the decision boundary, so it could as well be on the other part and be part of the minus, labeled as minus. So in some sense, the intuition we want to explain here is to say that the confidence in our classification is the distance of the point from the separating hyperplane. So what we want to do now is we want to find the hyperplane that has what is known as largest margin, right? So what we want to do is to find a line that separates pluses from minuses the most. So here is a simple example. The way we define the margin, we define the margin as a distance of the closest example from the decision boundary, right? So for example, on the case on the left, if this is our decision boundary, then the margin of this decision boundary is very small, right? Very quickly we hit a data point. While, for example, using the same data, here is a different decision boundary that has much larger margin. Right now here, margin gamma is much bigger, meaning the distance to the closest data point is much larger than on the case on the left. The reason why we define the margin in a way that we say what is the distance to the closest data point and maybe not what's the average distance or something like that is because this kind of makes sense intuitively, and also there is mathematical or machine learning theory that says that this is the right way to go about this and to define the margin as the distance of the closest example from the decision boundary. So now we will ask, why is maximizing margin gamma a good idea? And to do this, we really want to first compute what is the value of gamma. How can we compute the value of the margin? So the way we will reason about this is that first we need a simple fact from linear algebra. And it's a fact about the dot product, right? So if we think about what is the dot product between vectors A and B, then the value of the dot product is simply the length of vector A times the length of vector B times the cosine of the angle between the two vectors. So here is a simple picture illustrating this, right? I have a vector B, I have a vector A, and then the way I can think of the dot product is simply that I take A and project it down to B, and then the length of this projection is simply length of A times the cosine of the angle between the two vectors, and now I take this thing and multiply it with the length of B. So how can we think about the dot product or the inner product between two vectors? We can think of it in a sense of what is the length of the projection of vector A down to the vector b, and we measure this in the units of the length of vector b. So this is important because we can now go and actually compute what is the margin of a given data point. So let's think about it the following, right? We have our line, we'll call it capital L. We simply define this line as w times x plus b equals 0. And we also this cross here is the coordinate origin. Then another thing we have is that let's have this vector w that simply basically defines the line, and it has two coordinates, w1, w2, right? Now let's pick some data point A that has coordinates x sub a1 and x sub a2, right? Now what our goal is to ask is, what is the margin of this data point? How far is this data point from the separating plane? So how do we compute that? Let's first think of the location of the A simply as a vector pointing from the coordinate origin up to the point A. And simply, let's define another point M that is a point somewhere on the line. It doesn't matter. It's an arbitrary point on this line L. Okay? So now the question is, what is the distance between the line and the point A? So what we would like to do is we would like to find out what is the distance between the point A and the line, the green line L. And the way we compute this distance is simply, this is kind of the distance between the point A and the point H that is kind of closest to the point A, and H has to be on the line. So the way we can think of this is the following, right? So if we think about what is the vector between A to M, right? The way we compute this brown vector is to simply say this is A minus M, so we get the vector, and now we have to multiply this vector with W, right? In a sense that if we think about this multiplication, this will simply say if we project our vector A minus M on W, what is its length? So this is all okay and exactly as we want. But now we can start and expand the difference of vectors A and M. So if we do this, we get x sub A1 minus x sub M times W1 plus x sub A2 minus x sub M2 times W2. And now if we distribute the W inside, there is one important thing we have to remember, right? We remember that point M belongs to a line. So how is the line defined? The line is defined up here, which basically means that x times W, x sub M times W1 times x sub M2 times W2 equals minus B. So if we take these terms then and sum them together, their value should be minus B. So this means that kind of these terms cancel out and they can be replaced with the value of B. So the overall value is x sub A1 times W1 plus x sub A2 times W2 plus B, given the fact that we mentioned below. Now we can look at what is the value of this expression, and this expression is exactly W times A plus B, which basically means that the distance between the point A and the line L is simply the vector W multiplied by the coordinates of point A plus this offset term B. So what did we just do? We see that the margin or the distance is exactly the dot product of the vector W that is perpendicular to the line times the location of that point. So now that we know what is the value of the margin, we can already start formulating the problem of how do we find the best vector W? How do we find the separating plane that has the largest margin? So the way we do this is very simple, right? We already know how we will be making predictions. We simply take our vector W, multiply it by x, add b to it, and then based on the sign of this value, we either make a positive prediction or a negative prediction. So now we also just computed what is the confidence in our prediction, right? Confidence is simply the value of this whole term, right? And now, so in some sense, if we want to predict what is our confidence in prediction of the ith data point, kind of what is our margin for data point I, our gamma of data point I, is simply the confidence in our prediction times the class of that prediction. The reason why we are multiplying here with yi is very simple, because if our confidence is negative and the class is really negative, this means our overall confidence will be something positive. and if the two parts of this expression have mismatching signs, then our confidence will be negative, which means we made a misclassification. Okay? But now, given this in mind, we can simply say, what do we want to do? We want to find W, right? We want to find the separating hyperplane. We want to find the decision boundary such that all our training data, the margin of that given data point is as large as possible. So we want to find W where the smallest margin is as large as possible. So we can write this down as an optimization problem and say that our goal is to find gamma such that for every training example, the margin of this training example is at least gamma, right? We want to find the largest possible margin such that all the training examples have margin greater than gamma, and by finding such gamma, we are implicitly finding the W that achieves this large margin. So very simply, what is support vector machine doing, as we have done it right now? It's saying, I want to find the vector W such that it maximizes the margin, where here is a set of constraints that simply say the margin is simply the smallest value where our confidence in every prediction is at least that value. So to summarize what we learned so far about the support vector machine, we learned that the way the method works is that we want to find a separating plane or the decision boundary that maximizes the margin. We said that this is good both according to intuition as well as according to theory. In particular, the theoretical argument is based on Vapnik-Chervoninkin's dimension, and also it works well in practice. So the optimization problem that to find W that we identified so far simply says we want to find W such that our confidence in prediction over all the training example is at least gamma. So now the whole exercise will be, how do we go and find such W that maximizes our value of the margin, the value of gamma?